Hi, everyone. Thanks for coming to our talk. I'm David, and I'm here with Alex. We're both from the Kubernetes team at Atlassian here in Sydney. And today we're here to talk about securing untrusted workloads with Kata Containers. So if I can just get a quick hands up. So who heard of Kata Containers in the room? Oh, cool, okay, that's good. So I'll just give a little brief overview of Kubernetes Atlassian. So we've been running in prod for 3 years now, and we didn't have many tools at the time to deploy our Kubernetes clusters. So we really say we've done it the hard way. There's a tutorial, Kubernetes the hard way. Well, we've pretty much done that. We have a dedicated team to run those clusters. So we take responsibility for running the clusters and the worker nodes. So the good demarcation point would be the API server, where we provide API server for internal teams to consume and deploy their workload on top of the clusters. 50 clusters and growing, is that correct? That was, yeah. Well, we try to multi-tenant our clusters as much as possible, but sometimes it's not always possible for different reasons, security, networking, or things like that. But most of the time, we multi-tenant our clusters, and then we try to separate concerns. Like, for instance, we run Kubernetes clusters for job-based workload, and in some cases for stateless. One of the tools, the Atlassian offering that runs on top of our Kubernetes clusters is Bitbucket Pipeline. So if you don't know Bitbucket Pipeline, it allows you to deploy and build your code directly from where it is hosted on Bitbucket. So within a few clicks, you can actually start building your code and deploy it as well. So that runs on top of Kubernetes. And whenever you do a git push, for instance, each jobs or build will be a Kubernetes pod in its own namespace, and that runs on a pool of collocated nodes. So it's not really hard to understand why we're talking about, hard multi-tenancy here. Everything has to be isolated from each other. Every container needs not to know about the other. So if I have a job from a customer A, it needs to be completely isolated from another job from customer B. So really, security is something really critical in that cluster, and that's why we really talk about hard multi-tenancy. So we're always on the look for new ways of securing our clusters and securing those containers. So if I have a look at how the traditional containers, and when I say traditional containers, you probably understand better if I say Docker containers. We don't run Docker daemon anymore in our clusters, but it is effectively a Docker container. So the isolation works with kernel namespaces, and that's basically going to control what the process are going to be able to see or not see. So here I have 3 containers, process A, B, and C, with their own kernel namespaces, and then I have C groups, obviously, that's going to control what resources they can access. You can limit the CPU or the memory, for instance, and a bunch of other things. But the critical part here is those processes actually share the same kernel. So when you talk about securing those processes, the worst that could happen is having a container breakout. It's pretty rare, but it could potentially happen. So there's different mechanisms you can, or things you can do to secure those containers a bit further. And then it was just to talk about the best practices, what you can do for security. And then we do most of that, if not everything. Network policies, for instance, is a good one, where you're going to have your container A running from a customer, not going to be able to talk to container B. The rules are pretty simple in those clusters, for instance, where you're only going to be able to talk to the internet. You're going to be able to pull some code, do things like that, but you're never going to be able to talk to another container running that cluster or the underlying host. SecComp and capabilities is something that you should also need to do and then be very aware of. dropping capabilities and controlling what syscalls can be made on your clusters is something really critical. SE-Linux help where if there was something really bad happening and there was a container breakout, well, having those labels on your files, SE-Linux labels, would really limit the damage that could be done. And then finally, not running containers as root is a good thing for obvious reasons. Right, so as I said, the worst thing that could happen is really a container breakout. And then we have some interesting requirements in that cluster. And then one of those requirements is Docker in Docker. Developers love Docker in Docker. So you start a container for them with a build, and they want to be able to build their code in that container, but they also want to build their Docker images, and then they also want to push their Docker images, so like that build actually has something they can start using straight away. So in order to do that, we have to run Docker in Docker. You create a Docker container, and then you're going to run Docker container in that Docker. So that requires, well, root users, privilege mode, extra capabilities. It's a bit of a nightmare for a Kubernetes admin to secure it. So really, challenging security thing that Docker requirements. Another thing is CVEs. CVEs are really this big scary thing that you don't know what's going to hit you, and most of the time when they are announced, you actually have a fix already, and then you can push that fix. But it is the big scary thing here where you're running infrastructure with really untrusted workload, and well, you're trying to protect yourself against unknown CVEs. So this is where we really require that extra level of security where we think, well, the container isolation might not be just enough, and then we need another level, another layer of security. I think there's a good saying like security is like an onion, not because it makes you cry and it's hard, but because it's all about the different layers. So this is where we started with Kata Containers, and that comes straight from their website where it says the speed of containers and the security of VMs. Well, it almost sounds too good to be true, where you usually spinning up a VM will take you 30 seconds, a minute. Starting a container takes sub-second. Like if you have the image, starting a container is almost instant. Well, Kata kind of provides that. And it does that with running what they call micro virtual machine. So if I have a look at the isolation now, where I have the same traditional container isolation with my three same process, A, B, and C, that's sharing that Linux kernel, in the Kata container world, I have a micro virtual machine wrapping those containers. So each of my process A, B, and C, which are different containers, will have their own Linux kernel, A, B, and C. And then this is really where that extra level of isolation comes from, where you really have the hardware virtualization. On the underlying host, you have like the normal like Linux kernel. So how does it work? Well, Kata is OCI compliant. That means Kubernetes, or in that case, the kubelet, doesn't actually know it's going to start a micro VM to start your container. So there's a shim in between that's going to basically translate all the calls and then send them through a VSOC to an agent that runs inside that virtual machine. And that is that agent that was actually going to start those containers. So you have all the benefits of Kubernetes and the speed of it, and then you can kubectl exec and everything straight into that micro virtual machine with that extra level of isolation. So in order to start a Kata container, you have to tell Kubernetes how to start that container. So this is done with an annotation, and in a more recent version of Kubernetes, a runtime class. Kata can run on the same machine as a normal traditional container, which is a run-C container, basically. So you can run containerd, cryo, or even Docker alongside Kata containers that are going to run inside their own virtual machine. Kata Containers support different hypervisors, so there's a big buzz about Firecracker, which has been released recently by AWS, but we run the normal QEMU managed KVM-based virtual machine. So really, all you need to do is drop the packages for Kata Containers and annotate or use a runtime class for your pod, and then automatically Kubelet will just start your containers in that micro virtual machine. So we've done our proof of concept in about a week time, and that was super easy to do. And then we were like, well, can we actually run some of the most untrusted workload we have in the company on inside Kata containers? And with those Docker and Docker requirements and then things like that. We've proved that we could, and this is where I went to my boss and I said, look, I think we should definitely do this. And I handed it over to Alex, and then this is where all the challenges of making something production came in. And he's going to talk a little bit more about that.
Thanks, David. So as we were transitioning to Kata containers, one of the first hurdles that we encountered was disk performance inside the virtual machine. By default, Kata uses a system called 9pfs to share the root FS of the container, config maps, secrets, volumes into the VM. Any changes made inside the VM are propagated back to the host side and vice versa. This allows the kubelet to manage things like secrets and config maps from the host side and then have those changes replicated back into the VM. A benefit of using an old established protocol like 9pfs is that it is really reliable and it has really good compatibility with certain file systems. At one point, we were able to run an overlay file system on top of 9p inside that VM. But however, we soon got reports that builds were running really, really slowly in Kata containers versus natively in run C. In some cases, these builds were taking much longer and were performing worse than on the developer's laptop. So we started doing some performance benchmarks of the file system used by the containers inside the VM, and we quickly discovered why it was subpar. This is a sequential write of an 8 gigabyte file to the root FS, and it performed pretty poorly at 88 megabytes a second. For some perspective, consumer hard drives operate at around 150 megabytes a second when writing. If our goal was to provide a system from the early 2000s, then we definitely achieved that. And here's the same performance on my MacBook, which is considerably better. So it was really obvious now why developers were getting better performance on their laptops. So with some research, we discovered that Kata has support for plugging block devices into the VM. This is done by leveraging Device Mapper and a plugin built into Containerd that's fairly new. Rather than provisioning the Docker image as layers on the host with overlay FS and using that for the container's root FS, the Containerd plugin will create thin provision, copy on write block devices for the Docker image layers. With each block device, they are then plugged into the virtual machine and mounted into the correct location for the container's root FS. By using block devices, we avoid the encoding and decoding overhead of 9pfs while also maintaining that compatibility. That being said, we still have to rely on 9pfs for some sharing of directives and paths, but we've ensured that these are not in the critical path of builds. For example, the container secrets and config maps still use 9pfs, but these are small files where the penalty of 9pfs isn't as significant. Finally, we've ensured that device mapper blocks are provisioned on top of an array of NVMe SSDs to help boost performance. And so our sequential performance now looks like this, which is pretty good considering that it's inside a virtual machine and it's running on a multi-tenanted node. And we've found that our device mapper setup has been able to sustain 250,000 IOPS without issue, which is really ideal for a platform that relies on running a large number of builds on a single host. So the next challenge that we ran into was related to one of our requirements, moving to Kata. That was being able to run privileged containers in a secure fashion. As David mentioned earlier, this requirement would allow us to run Docker in Docker inside the VM, giving customers access to not only building images, but running those images within their build. Everyone's probably made a privilege container before, but if you haven't, this is what it looks like. You simply add privilege equals true to your security context for the container. And so along with having a correctly set up pod security policy, this will create the container with elevated privileges, all of the capabilities that you could ever want, and access to all host devices. And this is what we require to run Docker in Docker, letting people build images and run containers within their pod. So by default, if you don't have privilege set up, containers do not have access to devices on the host. But one of the things that privilege does grant you is read-write access to all of the host devices. If you ever needed to manage a disk on the host or a USB device from a container, then giving privilege is probably the easiest way to achieve this. But this ease of use can have some disastrous effects if not understood properly or done in a multi-tenanted environment. So having access to those devices on the host means you can not only read and modify the disks or file systems, but also file systems of other containers on the host itself. These capabilities in the wrong hands could result in data loss, secrets exfiltrated, and customer data stolen. For this example, I've actually listed out all of the device mapper devices that we're using in our Kata containers from the host side. And so when we run our privilege container on Kata, we also get all those privilege devices within our VM, which breaks the isolation that we thought we would have with Kata. So what does this let us do? Well, inside our privilege container, or as root is inside the VM, we can then mount and explore any file system mounted into the virtual machine. In this case, there was another container running on the host file system, which was DM25. This particular container was a Node.js Express app. I've then managed to mount DM25 to a path inside the VM with the Linux mount command. Once mounted, we can list any files in the container, including read-write if we wanted to. We can't view any processes, memory, or environment variables of that container, but being able to view another container's rootfs is pretty bad. As a remedy for this, we've contributed a flag to the CRI component within containerd to allow us to overload the default privilege behavior. With this flag, we can disable adding of those host devices for certain runtimes in containerd, and thus not mounting them into the Kata virtual machine. So overall, this was a really good learning experience for us, and some of our key takeaways are that we shouldn't assume isolation with anything, especially virtual machines. Performing an audit of the resources being exposed and shared to Kata helps uncover this problem. We did this from both the host side and also from within the VM, as it might not be evident on the host side that something is being shared into the VM. Finally, we are interested in improving the state of privilege in Kubernetes. This solution that we sort of hacked together isn't a great long-term solution. We'd like to see privilege in Kubernetes mature to a point where users have granularity over the extra privileges that privilege provides to a container. So that leads me to the final challenge that we've encountered, monitoring of containers running in Kata. So monitoring of containers, regular containers, is a fairly straightforward task when using runc. There are a few components, but essentially boils down to the kubelet exposing an endpoint with metrics of all the containers on the host. The kubelet then gets these metrics from CAdvisor, which in turn scrapes the C groups for the pods and containers on the host side for the actual metric value. C groups are utilized to control the resources for containers, and so CPU, memory, and network, and so on. As a result of them using to control the resources, they have very accurate and reliable metrics on the consumption of those resources. So when we look at that same metrics pipeline in the context of Kata, we run into a few problems. Initially, things look pretty good. Kubelet is able to query CAdvisor, which is in turn able to scrape the C groups for metrics. However, the metrics returned from C groups are missing individual container metrics due to the container process now running in a completely separate virtual machine and not on the host itself. The only process in that host C group is now the VM process, which is managing the VM. And so those metrics are now completely inaccurate. the metrics will measure the resources consumed to run the VM in total, but we've lost the ability to view individual containers. So with that, we looked for an alternative method for metrics collection. We'll have defined in Kubernetes 1.14, there is now a new metrics endpoint being exposed on the kubelet. The main benefit we see for this endpoint is it is now runtime aware. It will delegate its metrics collection off to the runtime, so whether you're running Kata or runc or some other runtime, the runtime itself is responsible for collecting metrics and shipping them back to the kubelet. For runc, nothing much has changed. It'll still look at the C groups on the host for resource consumption. And so when we go to get our metrics for our Kata pods, the runtime knows it needs to take a few extra hops or steps to collect the metrics for its containers. It will query the C groups from within the virtual machine rather than the C groups on the host. And finally, if you have mixed workloads running on the host, the endpoint works seamlessly with both runc and Kata container and whatever other runtime you want to run. So what's next for us with our journey with Kata? We've still got a few issues to work through and a few things that we're looking to utilize in the future. First is auto-scaling. I'm not sure if David mentioned it, but we require large metal instances to run these Kata pods. For a while now, we've been used to the start time of virtual instances in AWS, which can be up and running in a matter of seconds. But with metal instances, start times can be up to 10 minutes for a whole node to come up. With this, we need to ensure that we have enough capacity to absorb spikes in load, but also be really mindful of the cost of running these large instances. Another thing we're looking forward to is annotations that Kata provides to us. So this lets you add an annotation to your pod spec and then configure things that would normally be statically configured with Kata. So things like the CPU counts that are exposed to the VM, but with also like different kernel versions. So we could have a pod, two different pods on the same host running two different kernel versions if we wanted to test a new kernel. Finally, we're looking forward to using Firecracker as our virtual machine monitor. Firecracker is really appealing to us with its focus on security, performance, and the workload density, but unfortunately it does not fully support all the features that we require just yet. And that's all we had today. Thank you.
I think we have 2 minutes for questions, so if anyone has a question, I'll have a mic. I'll run around the...
Got one there.
Is there... Oh. Yeah, cheers, mate.
Hello. Thanks a lot for a great presentation. Question about your runtime engine. So basically, have you considered totally opposite direction? Instead of having huge machine with high latency and like a lot of pods on that, small machines, one container per machine. There are a few projects that can implement that. Thanks.
It's a really good question. Yes. One of the key features, like the key feature is the start time, where having those nodes already there and being able to pull, well, they already have the agents images pulled already, so the start time is almost instant with Kubernetes and having warm nodes, if you will. I think that was like really the trade-off. We might reconsider that with new things like Fargate, for instance, where eventually we will be able to run a container in its own virtual machine or KubeVirt, but they're not there yet. So that's why we had to go the Kata route to run those privileged containers in their own kernel. So it's not there yet, but yes, absolutely in the future, I think with the start time improving, we will be able to.
Any more questions?
Cool. Well, we're almost out of time. Thanks all for coming.
Thank you.
And,